Hello and welcome to this video which I have called a very difficult maths problem. I only used that title so that I thought it might generate some interest. What I meant is a very difficult maths problem for me. In fact, to be fair, I have discussed this problem with one or two of my friends and colleagues who are mathematicians, and for the moment we have not been able to come up with a solution. So I'm hoping somebody on YouTube will either know a solution or can solve it. And there are many math enthusiasts on YouTube. So I'm hoping that I'll get a result by sharing this question with you. I will share in here the work I've done already and what pointers I have had, which is not that many, but I will share it nevertheless. Anyway, to start with, this is the problem. First, I have to define what I call an under-over shuffle. By the way, this has got nothing to do with playing cards. I use the cards as a demonstration. An under-over shuffle means if you have a deck of cards, you take the first card, you call this under, then the next top card goes over, the next top card goes under, and then over, under, over, like this. So we call this an under-over shuffle. Under, over, under, over, under, over, under, and so on. So that's the definition of what I've called it an under-over shuffle. Now the question is this, demonstrated by a few examples. Supposing, let me take a few cards out, 5, and I think maybe 6, 8, maybe. Anyway, let's say I have two cards. Where's number 2? Here. 2 here. If I have two cards, ordered 1, 2, that's the under-over shuffle. That's one cycle. Under-over 2 cycles. After 2 cycles, I restore the original arrangement. Now, if I have 4 cards, in the order that you see, 1, 2, 3, 4, I do 1, 2, 3. Now, after 3 cycles, I'm back to the original arrangement. Now let's try 6 cards. I have 1, 2, 3, 4, 5, 6 cards. I go under, over, under, over, under, over. That's 1. That's 2. This is 3. This is 4. This is 5. 6. After 6 cycles, I've restored the original order. Now, one would expect as you increase the number of cards, this will get larger and larger. Now, I have to say, we're only dealing with even number of cards. So it's either 2, 4, 6, 8, etc. So with 8 cards, you would expect to get more than 6, because with 6 cards, we got 6. So I do 1, 2, 3, 4, and we see after 4 cycles with 8 cards, the number of terms is the original arrangement is restored. Now I have tested this for several even number of cards like 8, 10, 15, etc. So far, this is what I have discovered. And this is not a proof. This is just a imperial information. Now, what I have discovered so far is that if the number of cards, call it K, if K is a number of cards, this is a power of n, a power of 2. If the number of cards that I start with is a power of 2, I will need n plus 1 cycles to restore the arrangement to the original arrangement. For example, for 2 cards, which means it's 2 to the power of 1, I needed 1 plus 1, 2 cycles. For 4 cards, which is a 2 to the power 2, I needed 2 plus 1, which is 3 cycles. Now, let's leave 6 out for a moment. For 8 cards, which is 2 to the power of 3, we needed 3 plus 1, 4 cycles. Now, I have tested it up to even 64 cards. Now, 64 is 2 to the power 6. And for this, I need 7 cycles. But for 6, we noted we needed 6. Any number in between, I get different number of arrangements, so a different number of cycle requirements. And so far, I have not been able to find a direct relationship between the number of cards that I start with and the number of cycles required to arrive at the original arrangement, to restore the original arrangement. Now, I have used a spreadsheet to simulate some of this, which I will show you in a minute. But the idea here is that if anyone can contribute, can help, or perhaps knows a solution, please leave a comment in the comment box, because I would appreciate it. I've been curious about this question for several months, but ever since I was a little boy, I knew that for a pack of 52 cards, for example, playing cards, 52 cards, you need 12 cycles to restore the original arrangement. Now I'll show you what work I've done so far using a spreadsheet. Now here I'm showing you on a spreadsheet. This is the number of cards that I start with. It's 2. That must be 2 here, I think. 2, 4, etc. Now, the cells that are highlighted in blue are the cells which are powers of 2, including this one. This is 2 to the power 6, which is 64. And we notice that for the powers of 2, my empirical formula, which if it's 2 to the power n, we need n plus 1 iterations. So for 2, we need 2 cycles. For 4, we need 3. For 8, we need 4. For 16, we need 5. For 32, we need 6. For 64, we need 7. But I've tried these numbers in between. Like, for example, for 6 iteration, I get 6. For 6 cards, I get 6. For 10 cards, I get 6. For 12 cards, we need 10. 14 is 14, 18 is 18, 20 is 10 again, 22 is 12, 24 is 21. There's no rhyme and reason, nothing that I've managed to find out. I've even plotted the graph. The graph is something squiggly like that. And if I come all the way back here, this is one I've done, which is for a full deck of cards of, say, 52 cards, and with 52 cards, this is the first iteration. Here is this 1, 2, 3, 4, 7, 8, 9, 10, 11, 12. On the 12th cycle, everything is restored back to the original arrangement. So here's the challenge. If anyone can find out why, well, can find out a formula so that given n number of cards where n is an even number, and we do the under over shuffle as shown earlier in the video, how many cycles of this shuffling do we have to do to restore the original order of the cards? Please give this video a like, and as I said, if you can give me a solution, find a solution, refer me to a solution, I would be very grateful.